NEC 517.14 specifies that a grounding electrode conductor, sized according to Table 250.122, must be connected to both the grounding electrode system and the equipment grounding terminal, or the enclosure, of the panel board. NEC 517.14b mandates that grounding electrode conductors from all panel boards and switchboards are interconnected in accordance with 250.122 and connected to the grounding electrode system. In simpler terms, the grounding electrode conductor originating from each panel board has to be connected to the grounding electrode system. This grounding electrode system can be common to all the panel boards and switchboards within the hospital. Moreover, the grounding electrode conductors that come from all the panel boards and switchboards must be interconnected, and this interconnection has to comply with the standards outlined in 250.122. Now, to address the specific situation of a multi-floor hospital, bonding the electrical systems at their origin, which in the example is the basement, and then running an insulated bonding conductor fulfills the requirements of both NEC 517.14a and NEC 517.14b. This approach ensures that all panel boards are properly grounded and interconnected as required by the code. Bonding at each individual floor is not a necessary step. In fact, introducing additional bonding points at each floor level could potentially create unwanted ground loops. Ground loops can introduce noise and interference into electrical systems, which can be problematic, especially in sensitive patient care areas of a hospital. Therefore, the preferred method is to establish a solid grounding and bonding system at the source and then distribute that grounding throughout the building using appropriately sized conductors. Remember to always consult the most recent edition of the National Electrical Code and to seek the advice of a qualified electrical engineer or inspector to ensure full compliance with all applicable regulations and best practices. Table 250.122 provides the minimum size requirements for equipment grounding conductors for grounding raceway and equipment. The size of the equipment grounding conductor is based on the rating or setting of the overcurrent protective device in the circuit ahead of the equipment. For example, if the overcurrent protective device is rated at 20 amps, Table 250.122 requires a minimum equipment grounding conductor size of 12 American wire gauge copper or 10 American wire gauge aluminum. If the overcurrent protective device is rated at 60 amps, the minimum equipment grounding conductor size is 10 American wire gauge copper or 8 American wire gauge aluminum. If the overcurrent protective device is rated at 100 amps, the minimum equipment grounding conductor size is 8 American wire gauge copper or 6 American wire gauge aluminum. It is important to note that these are minimum sizes and larger conductors may be required depending on the specific application and installation conditions. Section 250.122 provides additional requirements and exceptions to the minimum size requirements. It is crucial to refer to the complete table and related code sections to ensure proper grounding and bonding of electrical systems. In hospitals, maintaining a reliable grounding system is critical for patient safety and the proper operation of sensitive medical equipment. Grounding helps to minimize the risk of electrical shock and ensures that fault currents are safely carried back to the source, allowing overcurrent protective devices to trip and to energize the circuit. The grounding electrode system typically consists of a combination of grounding electrodes such as ground rods, metal water pipes, and building steel. These electrodes are connected together to form a low-impedance path to ground. The grounding electrode conductor connects the grounding electrode system to the electrical system at the service entrance. This conductor must be sized appropriately based on the size of the service entrance conductors. Inside the panel boards, the equipment grounding bus provides a connection point for equipment grounding conductors. These conductors run with the circuit conductors and connect to the metal enclosures of equipment and devices. This ensures that any fault current will flow back to the source through the equipment grounding conductor, tripping the overcurrent protective device. Bonding is the process of connecting together all non-current carrying metal parts of the electrical system. This includes metal conduits, enclosures, and equipment frames. Bonding creates a low impedance path for fault current, which helps to minimize the voltage potential between different metal parts. This reduces the risk of electrical shock and ensures that fault currents are effectively cleared. In addition to the general grounding and bonding requirements, hospitals have specific requirements for patient care areas. These requirements are designed to provide an extra level of protection for patients who may be more susceptible to electrical shock. One key requirement is the use of isolated power systems in critical care areas. Isolated power systems use a special transformer to isolate the electrical system from ground. This reduces the amount of leakage current that can flow through the patient. Another requirement is the use of ground fault circuit interrupters, or GFCIs, in wet locations and other areas where there is an increased risk of electrical shock. GFCIs are designed to detect small amounts of leakage current and quickly de-energize the circuit. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems in hospitals. It is important to follow all applicable codes and standards and to use qualified electrical professionals to install and maintain these systems. Remember to consult the latest edition of the National Electrical Code and to seek guidance from experienced electrical professionals to ensure compliance with all applicable requirements. The National Electrical Code, or NEC, is a comprehensive set of standards for the safe installation of electrical wiring and equipment. It is updated every 3 years to reflect changes in technology and best practices. The NEC is adopted by many states and local jurisdictions and is widely recognized as the standard for electrical safety in the United States. Article 517 of the NEC covers the specific requirements for healthcare facilities. This article addresses the unique electrical safety challenges presented by hospitals and other medical facilities. It includes requirements for grounding, bonding, isolated power systems, and other specialized electrical systems. Compliance with Article 517 is essential for ensuring the safety of patients, staff, and visitors in healthcare facilities. Grounding electrode conductors play a vital role in providing a safe path for fault currents to return to the source. A grounding electrode conductor connects the grounding electrode system to the electrical system, providing a low-impedance path for fault currents. The size of the grounding electrode conductor is determined by Table 250.66 in the NEC, which is based on the size of the service entrance conductors. The grounding electrode system typically consists of a combination of grounding electrodes, such as ground rods, metal water pipes, and building steel. These electrodes are connected together to form a low-impedance path to ground. The grounding electrode conductor must be connected to the grounding electrode system at a point that is accessible and permanent. This connection is typically made at the service entrance or at a separately derived system. It is important to ensure that the grounding electrode conductor is properly sized and installed to provide effective grounding protection. Improperly sized or installed grounding electrode conductors can compromise the safety of the electrical system and increase the risk of electrical shock. Equipment grounding conductors, or EGCs, provide a path for fault currents to return to the source from non-current carrying metal parts of equipment. The EGC is typically a wire that runs with the circuit conductors and connects to the metal enclosure of the equipment. In the event of a fault, the EGC provides a low-impedance path for fault current to flow back to the source, tripping the overcurrent protective device and de-energizing the circuit. The size of the EGC is determined by Table 250.122 in the NEC, which is based on the rating of the overcurrent protective device protecting the circuit. It is important to ensure that the EGC is properly sized and installed to provide effective fault current protection. A properly sized or installed EGC can increase the risk of electrical shock and equipment damage. Bonding is the process of connecting together all non-current carrying metal parts of the electrical system to create a low-impedance path for fault current. Bonding helps to minimize the voltage potential between different metal parts, reducing the risk of electrical shock. Bonding is typically accomplished by connecting metal conduits, enclosures, and equipment frames together with bonding jumpers or bonding conductors. The size of the bonding jumpers or bonding conductors is determined by Table 250.102 in the NEC, which is based on the size of the largest ungrounded conductor in the circuit. It is important to ensure that all metal parts of the electrical system are properly bonded together to provide effective fault current protection. Improper bonding can increase the risk of electrical shock and equipment damage. Ground loops can occur when there are multiple paths for ground current to flow. This can create unwanted circulating currents that can cause noise and interference in electrical systems. Ground loops can be avoided by ensuring that there is only one path for ground current to flow. This can be accomplished by using a single-point grounding system where all grounding connections are made to a common point. In a single-point grounding system, the grounding electrode conductor is connected to the grounding electrode system at a single point, and all equipment grounding conductors are connected to a common grounding bus. This prevents ground current from flowing through multiple paths and creating ground loops. Isolated power systems are used in critical care areas of hospitals to reduce the risk of electrical shock to patients. An isolated power system uses a special transformer to isolate the electrical system from ground. This reduces the amount of leakage current that can flow through the patient, minimizing the risk of electrical shock. Isolated power systems are typically used in operating rooms, intensive care units, and other areas where patients are particularly vulnerable to electrical shock. Ground fault circuit interrupters, or GFCIs, are devices that are designed to detect small amounts of leakage current and quickly to energize the circuit. GFCIs are typically used in wet locations and other areas where there is an increased risk of electrical shock. When a GFCI detects a ground fault, it quickly trips the circuit, preventing electrical shock. GFCIs are an important safety device that can help to protect people from electrical hazards. Electrical safety is a critical concern in hospitals and other healthcare facilities. Patients in these facilities are often more vulnerable to electrical shock due to their medical conditions or the use of medical equipment. It is important to follow all applicable codes and standards and to use qualified electrical professionals to install and maintain electrical systems in healthcare facilities. Proper grounding, bonding, and the use of safety devices such as GFCIs and isolated power systems can help to minimize the risk of electrical shock and ensure the safety of patients, staff, and visitors. Regular inspections and maintenance of electrical systems are also essential for identifying and correcting potential hazards. The information provided here is intended for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and standards.